Hi folks, chapter 4 continued. Here goes. A 65 kilogram person stands on a scale in an elevator. What is the apparent weight when the elevator is accelerating upward, moving at a constant speed, and accelerating downward? So here goes. For the first part, the net force on the person is going to be a combination of the force to make them accelerate upward plus the force of gravity. Both forces are acting on the person. So the net force is going to be their mass times the force of the acceleration plus the mass times the acceleration of gravity. So if we have a 95 kilogram person and they're accelerated upward at 1.8 meters per second squared plus their 95 kilograms mass times the acceleration of gravity, 9.8 meters per second squared. When you add all that together, they're going to end up with a net force of 1,100 newtons is going to be the net force on them. Okay? All right. That is going to be their apparent weight. That is going to be their apparent weight, what their bathroom scale is going to read. Not just their weight, but also that this extra force of acceleration is going to add to that weight. What happens when they're at a constant speed? Well, when they're at their constant speed, the force acting on them from their elevator is going to be equal to the force of gravity, and the force of gravity on them is simply mass times acceleration of gravity, or their 95 kilograms times the 9.8, excuse my voice, meters per second squared, and that should be equal to 931 newtons. Now for part C, when they are just starting to go back down again, the net force on them is going to be the force of gravity minus a fraction of their weight that is no longer supported by the elevator. They have to be accelerated in a downward direction. So minus the force of acceleration in the opposite direction so that they are no longer supported. So this is going to be mass times acceleration of gravity minus their mass times that negative acceleration of the elevator. So we already know force of gravity is 931 newtons minus their mass, 95 kilograms. The acceleration downward, we're told, is 1.3 meters per second squared. So 931 newtons minus another 124 newtons for these, and that ends up being a weight on their elevator of I can add 807 newtons. So they're going to weigh just a smidge less for that fraction of a moment. All right, next problem. Here goes. A 1.14 times 10 to the 4th kilogram lunar landing craft is about to touch down on the surface of the moon. At an altitude of 165 meters, the craft's downward velocity is 18 meters per second. In order to slow down the landing craft so that it has a final velocity of 0 just before hitting the lunar surface, what upward thrust must be provided on the craft's retro-rockets? Recall that the acceleration of gravity on the surface of the moon is about 1/6 what it is on Earth, or 1.6 meters per second squared. So, first off, we have to look at what we've got down here. Now we know the mass of the landing craft is 1.14 times 10 to the 4th kilograms. It's touching down on the surface of the moon at it's 165 meters above the surface. So it's got 165 meters is its displacement above the surface of the moon. It has a original velocity of 18 meters per second, and it wants to land with a velocity of 0. In order to slow down the landing craft, we want it to have a final velocity of 0, and we want to know what upward thrust, meaning what force, must be supplied by the retro rockets so that it has basically no velocity when it hits the ground. Well, in order to do that, we need to know what upward acceleration the whole retro-rocket system has got to supply in order to counteract the lunar acceleration of gravity. So this is going to be a multi-step problem. First thing we're going to do is we're going to take this information and use a kinematics equation, and we're going to find what sort of a acceleration the rockets are going to have to provide to counteract the acceleration of the moon's gravity. So using displacement, original, final, and acceleration of gravity, which equation does that kind of pop out of my brain? That looks like Vf squared is Vo squared plus 2ax. If I solve for A is final velocity squared minus original velocity squared divided by 2x. Final velocity is going to go to 0, so acceleration is going to be minus original velocity of 18 meters per second, quantity squared, divided by 2 times 165 meters per second. So when I throw all of that in my calculator, I end up with 0.981 meters per second squared. And this is a negative, and what does that mean? That means that this is going to be slowing the rocket down as it is descending down to the surface. Now, if I have that, now we can use this to calculate the thrust of the rockets. So let's continue this forward, and we're going to have to come up with a picture and the forces on my rocket. So the force of gravity is going to be pulling downward, and we're going to have a force of the rockets pulling it upward, and we're going to have these equal M and A. So remember, that's the net force that is going to make the mass accelerate. And my net force in this situation is going to be force of the rocket upward minus the force of gravity downward is going to make the rocket engine mass accelerate. Now, the force of thrust of the rocket, that's what we want to know. So this is going to be equal to, we're going to, FR for force of rocket, is going to be mass times rate of acceleration of the rocket, plus, I'm going to pull this to the other side, plus force of gravity is mass times acceleration of gravity on the moon. So the mass of the rocket is a big beast, 1.14 times 10 to the 4th kilograms. We were told that in the problem. How fast does it have to accelerate? Well, we just calculated that right up here. So times 0.981 meters per second squared, plus, and I apologize, I'm going to have to put this on the line below, times the mass of the rocket, which is 1.14 times 10 to the 4th kilograms, times the acceleration of gravity on the moon, 1.6 meters per second squared. And when I do all of the math, I end up with the force of the retro rocket ends up being about 29,400 newtons of force. That is a pretty decent little rocket. That's not as much force as it would have to be because there's not a lot of gravity on the moon. All right, that will do for this one, and we will see you later. Bye-bye.